So I posted your exam grades. I put a notice on Moodle. Just want to say that there was a curve to the exam. That 10 points was added into the exam. So whatever your grade is on Moodle, that's what your grade is. Later, I'll actually post the quiz itself so that you'll be able to see what you answered and which ones you got incorrect. And then I'll also post a video and a PDF of the exam so you can review that. We can talk about it later. If you want to come by my office, we can chat about it. But I would wait till those things are posted so you'll know which ones you missed. I also posted your extra credit. Right now, the maximum that you can have, we only had 8 things, so you can only have 16 extra credit points. And some of you have that. I just want to let you know that once you get to 20, you can't go any higher than that. I would recommend that you keep coming to the help sessions. I think they're useful just to help you stay on track of what we're doing. But you can't get any more credit for that. And if you're low in your extra credit, you still have a lot of opportunity to get extra credit. We have those help sessions almost every week, and so you'll have lots of opportunity to get that. And then also the class participation. I just took a look at the class participation. I rescaled it and thought about sort of what I expected for that. So as of now, if you have 50% or less for class participation, that's a problem. We need to address that. It might be that your clicker hasn't been working right, or maybe you were sick, or you've been out. And if you have some excused reason for being out, then please let me know. But otherwise, if it's below 50%, we need to fix it. So come by and see me if that's the case. I want everybody to get that credit. That's 50 points. You shouldn't be throwing it away. It's not a huge part of your grade, but it can impact your grade. It's 50 out of 700. That's the percentage. We have a help session on Friday. It'll be at 2. I'll send a reminder about that later. And then your drop day. Listen, I know exam 2 is tough. I told you it was going to be tough. And some of you did quite well on it, but others didn't do well on it. And so I just want to encourage you that there's still a lot left in this class. And I think that as you see today, that you'll see that chapters 5 and 6 are quite a lot easier. I believe that they're quite a lot easier than chapters 3 and 4. And students usually do a lot better on the exam 3 than they did on exam 2. I also want to point out that your drop day isn't until October 21st, and that's a full week after our exam 3. So if you're thinking about dropping the class, don't. Just hang in there until we get to our exam 3. And we'll have a couple of quizzes in between there. You'll begin to see, I hope, some drop quizzes. As you do well on the quizzes, that you'll have, okay, well, I can get rid of that quiz and that quiz, and maybe that quiz too. Okay, so just hang tight. If you're not doing well, come see me. The tutoring center is awesome. It's only $25 a semester. They offer tutoring in chemistry, physics, calculus, biology. They offer tutoring in all of your subjects that you're taking this class. Okay? Questions? Yeah.
Do we still have the cumulative final?
Yes. Yes, we'll have a cumulative final. It's on, for y'all, what's it, 4M, November 18th. Anything else, y'all? Any other questions? Yeah. Oh, the class? Oh, no. Okay. Oh, yeah. I knew it was going to be a hard exam. It was hard. Was it tough? Yeah. Tough exam. Even if you knew what you were doing, it was tough. All right. I will tell you there were no perfect scores. The top score was missing 1, but with the curve, they have over 100%. All right. I like to see perfect scores. Oh, the one other thing, on the website, I pointed this out before, but there's a grade calculator. If you click on that and download it, and then open it in Excel or Numbers or whatever you use, you can put in your grades and just figure out what it is that you need. So you would put in the grades that you already have, exam 1, exam 2, and then some of your quizzes, and you can just, it'll calculate what your overall average is. So that's just a good way to sort of play around with what you need in the class to make a whatever. All right. So I didn't tell you to watch the videos for chapter 5. You just finished your exam, and I don't know, just didn't figure you wanted to. So I'm going to give you a quick little primer on chapter 5, and then we're going to work through chapter 5 today. We might spend a little bit more time on Friday, but not much. This will be pretty much it. Make sure this week that you're watching the videos for Chapter 5 and that you're practicing all the different types of questions that you might see on Friday. We'll do that today too. We'll get through all of it. It's usually a short chapter. Usually only spend about 1 or 1.5 classes on Chapter 5 anyway. All right, so with Chapter 5, these are just sort of some of the things that you're going to see. First is the idea of work. That if, not word, work. If I have a force acting over a distance, then the work done by that force is equal to F times D. If I have a force that is acting at some angle to a displacement vector, the work done by that is equal to FD times cosine of theta. So this is our equation for work. It's equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Now, the force and displacement in this case, what is the angle between these two vectors? They're in the same direction, so the angle is what? Is 0 degrees, and the cosine of 0 is 1. So this equation applies for these forces, where the cosine theta term would just go away. This is a general equation. It's valid in all cases. In some cases, we can have a force in this direction and a distance in this, or displacement in this direction. In that case, the angle theta would be equal to 180 degrees. And the cosine of 0 is 1. The cosine of 180 is, no, is -1. The cosine of 90 is 0. The cosine of 180 is equal to -1. So in this case, I would have work equals to FD cosine of 180 or negative FD. So that work, that would be a negative work. We'll talk about what that means. The other thing that we're going to talk about is energy. We're going to talk about 3 different types of energy. You'll see this when you do them in the videos. There is kinetic energy, potential. Well, there's 2 different types of energy, kinetic and potential. And then within the potential, we're going to talk about 2 different types, which is gravitational potential and elastic potential. Gravitational or kinetic energy, rather, KE, is equal to 1/2 mv squared. Gravitational potential energy, PE, is equal to mgh. And then elastic potential, PES, I'll call it, is 1/2 kx squared. Okay? So those are the 3 different types of energy, really 2 broad categories. And then within potential, there are 2 different types. I'll work some problems in just a bit on that. There is a theorem called the work energy theorem. And the work energy theorem says that if I do work on an object, I change its energy. If I apply a force over a distance, then it changes the energy of that object. And we'll see some problems on some of the old exams regarding that. And then finally, there's the conservation of energy. And the conservation of energy says that the initial energy is equal to the final energy. There are a couple of small details that you'll pick up when you watch the videos having to do with conservative and non-conservative forces. But for now, we'll just say that the energy in a system is always conserved. It's always the same. That is to say that the kinetic energy plus the potential energy will never change. That whatever kinetic and potential I have in the initial state, I'll also have in the final state. And that's a really powerful tool when you're looking at objects moving through a gravitational field, moving with relation to the Earth. Okay, those are really the only big ideas. You might have seen some of these. You should have at least seen energy. You might not have seen conservation of energy, but I'm sure you've seen energy in high school physical science. Let's go into the chapter. Let's actually go to the homework first. At the end of the chapter, there's homework questions. Here I have a shopper that's pushing a supermarket, and they push a cart with a force of 35 newtons down at an angle of 25 degrees downward. So this angle, theta, is equal to 25 degrees down a 50-meter length of aisle. And I want to know, what is the work that's done by that shopper on the cart? How much work has been done? To find the work, I would say that it's equal to FD cosine theta. You'll probably have a problem like this on the test, where my force is 35 newtons. My distance that it travels, or my displacement, is 50 meters times the cosine of 25 degrees. And so that's going to be the work of the object that's been done. Aaron, what you get on that? Okay, so 1,600 joules. Let me just say something about units, since I'm just introducing the units for this. The unit for work is the Newton meter. 1 Newton meter, right? It's a force, which is a Newton, times a displacement, which is a meter, so it's a Newton meter. However, the unit for energy, this is work, the unit for energy is the joule. But because we have this close relationship between work and energy, that is, if I do work on an object, I do what to its energy? I change it. I can increase it or decrease the amount of energy that that object has. That's the work energy theorem. Work changes the energy of an object. Because of that close relationship, I like to use joules for work as well. And plus, we'll see this unit again, the Newton meter, when we get the rotational motion, when we start dealing with torques. So I'm going to use joule most of the time, but I might slip into Newton meters. But just know those are the same. Now, let's say that this cart has a mass of, I don't know, 50 kilograms. And I want to know, what is the speed of this object at the end of this 50 meters? What is its speed? This is not asked in the question. I'm just asking you a different question. I know the work that's been done on the object. And I know that work causes a change in energy as I have this cart pushing with that force of 50 meters at an angle of 25 degrees or whatever. What kind of energy am I giving it? Am I giving it potential energy, or am I giving it kinetic energy? I'm giving it kinetic energy. That's the energy of motion. So whatever work I do on this will go into kinetic energy. So work will equal to 1/2 m times v times squared, v squared. So I can say 1,600 joules, which is the amount of work that I've done, is equal to 1/2 of 50. And I can solve that for v. 3,200 over 50. Take the square root of that. 80? No, not 80. 8? Is it 8? Yeah. Okay. That's a good work energy problem. I would see both types of those problems on the quiz or in the exam in a couple of weeks. By the way, I'd expect definitely chapters 5 and 6 on the exam. They're both pretty short chapters. Probably a little bit of chapter 7. Probably 5, 6, and 7. All three of those are really short chapters. All right. Questions? Concerns? Yeah, Jonas? Huh? 32. 3,200. Oh, I divided 16 by 1/2. I divided both sides by 1/2. and 1600 divided by a half is 3200. Or multiply both sides by 2. And then I divided both sides by 50, and now I took the square root. All right, I'll come back to this. Okay, let's look at number 4. Just disregard that this is on a trampoline. The trampoline just sort of complicates your thoughts of it. Just imagine that you have an athlete that jumps upward with a speed of 9 meters per second. That's pretty fast, but they jump upward with a speed of 9 meters per second. And I want to know how high the athlete goes, and then also what is the speed of the athlete when she's halfway up to her maximum height. We've done this problem. We did it in chapter 2, where if I have an object that has an initial speed of 9 meters per second, it goes up, and then it comes back down again. In order to solve that problem, we'd have to find how long does it take to get up to the top of the trajectory, and then turn around and come back down. It's kind of a complicated problem. There are several steps to it that we did in chapter 2. But we'll find in this chapter that we can do it in a much easier way. That I can say that the energy down here, I'll call it EI, is equal to the energy up here. We'll call that EF. EI is equal to EF. The initial and final states have the same amount of energy. Now, what kind of energy does she have at the bottom? Potential, kinetic, or both? And let me remind you how we calculate these. Kinetic, which is the energy of motion, is 1/2 mv squared. And potential, which is the energy of position, is mgh. Potential energy is like if I have an object in this position, does it have the potential for motion? Does it? Does this have potential for motion? Sure, right? If I let it go, it moves. So at the bottom, which does it have? Kinetic, potential, or both? Okay, it has kinetic for sure, but does it have potential? Now, let me write in the heights here. Here, the height is, well, we don't know. That's what we want to find out. But down here, the height, because it's our initial point, we're going to say that that's equal to 0. So does it have potential energy? No, it doesn't have potential energy, because at that point, at the ground level, that's our initial point. We call that h equals 0. So at the bottom, it only has kinetic energy. At the top, it has kinetic, potential, or both. Only potential, right. So our initial state would only have kinetic. Our final state would only have potential. Now, really what I'm doing here is that the conservation of energy looks like this, but these terms are going away because they're both equal to 0. The potential energy initially is equal to 0 because h equals 0, and the kinetic energy at the final state equals 0 because v equals 0. So when you see these problems, you'll have to think about, okay, what is the kinetic and what is the potential? And is it 0 at this position? Now, this problem becomes pretty simple, actually. I say that the kinetic energy is 1/2 mv squared. I know that v. And the potential energy is mg times h. I can cancel out my masses. They aren't relevant. And then I find h. H is equal to 1/2 of v squared over g. 1/2 of 9 squared over 10. 4.1 meters. Okay? What about, we'll see a problem like this on the old test. What about part 2 of this problem? That is, what is the speed of the athlete at halfway? At right here. What is the speed? Well, at that point, does she have potential, kinetic, or both at a point halfway? Think about it, don't say anything yet. No, it has potential, right? Is that potential? Does she have potential energy at this point? What is H? Is H 0 at this point? No. So it has potential. Now, to answer whether or not it has kinetic, I have to think about what is the speed of the athlete. Does she have a speed at this point? Yeah. So does she have kinetic? Yeah. So, okay. So this problem is different from the first one because here I'm going to have both kinetic and potential energy. So this problem would be, well, I could say the kinetic energy initial is equal to the kinetic energy, I'll say M for midway, plus the potential energy M for midway. And I work it the same way. 1/2 of M, I'm just going to put the value in here, 9 meters per second squared equals 1/2 of M times V squared plus M times G times H, which is going to be 2 meters. Because that's half of 4.1, or that should be 2.1 meters, 2.05. And then you would solve that for V. I'll leave you to do that on your own, but we'll see another problem later that's really similar to this. We'll do it on a clicker. That idea is the conservation of energy, that the energy in an initial state is equal to the energy at every other state within that system as it progresses through time. Questions? Concerns? No? Let's see. This is another one that's similar to that. That one's similar. All right, let's go up into the chapter and we'll do some of the quick test problems. I think we've done most of the types of problems. Let's try this one. Which force on these, this is on page 108. Which of all of these forces, all of these blocks are moving to the left. So all these blocks are moving with a displacement in this direction. And further, all of these forces have the same magnitude. So which force does no work? Which of these forces does no work at all? All right, let's wrap it up here soon. Stop at 1 minute. All right, very good. A is the right answer. The one where the force and the displacement are perpendicular, that means that the angle theta is 90 degrees. And since W is equal to FD cosine theta, cosine of 90 is equal to 0. All right, so this would give us a work equal to 0. And plus you can think about it that force, which is acting upward like the normal force in this chair, that normal force is not causing me to move in either direction. So that force is doing no work. It's not causing any displacement in any direction. So, good. Number 1 is right. Hey, how does Moses make tea? He brews it. Because he is a Hebrew, right? Like he's an ancient Hebrew. Yeah, you got it. Okay, which force does negative work? Which of these forces does negative work? Moving to the left, I want to know which force does negative work. All right, good. Ask your friend if you're not sure. Ask your neighbor. I'll stop at 35. Okay, good. C is the right answer. That's correct because my force is in this direction and my displacement is in the opposite direction. Can you think of any forces that act opposite the displacement? What's a force? The frictional force. Friction is a great example of a force that acts opposite the direction of motion, right? You move one direction, the friction is in the opposite direction. Friction almost always does negative work. The idea of negative work, we saw this with the work energy theorem, that work is equal to a change in energy. Work is equal to a change in energy. And so when I talk about positive or negative work, it doesn't refer to a direction. Because work is what type of quantity? Vector or scalar? It's a scalar quantity, so it doesn't have any direction. So when I give it a negative, it doesn't mean in the negative direction. It means that that work or that force is actually taking energy away from us. And friction is a great example of a force that takes energy away from an object. So it does negative work is C. And then I'm not going to do 3 and 4, but which force does positive work? Okay, B does positive work, but be careful because D also does positive work. So both of these, B and D, do positive work, but the force that does the most positive work is what? B or D? B does more positive work than D, because with D, you have two components of this force. One is to the left and one is up. The upward force doesn't do any work at all, because the angle between the y component of this force and the displacement is 90 degrees, and so that gives us 0 work. Let's try this one. Hopefully this is a gimme. All right, let's have 10 more seconds. We'll stop at 1:15. 1:15. Okay, awesome. So here, just like we did before, work is equal to F, that's 40 newtons, times D, which is 25 meters, times the cosine of the angle, which is going to be cosine of 60. And that gives me 500 joules. All right, so the work done on that is 500 joules. I went to this meeting the other day. It was for the vegetarian club. Anybody in the vegetarian club at Nichols? No? I met this young woman there, and she said that she had met me somewhere. I don't know where, because you know what? Never seen her before. Oh, okay. She watched these videos this week as you're preparing for the exam. Let's try this one. This is asking for the kinetic energy. You have this object that follows a trajectory like this, and I want to know what is the kinetic energy at the top there. You have to think back to our projectile motion to figure out what is the velocity at the top. All right, let's try to wrap up in 10 seconds. I'll stop at 2:20. It's 5 seconds. All right. Okay, so at the top of the trajectory, I know that the velocity is only in the x direction. So I need to first find out what is Vx, and that's going to be V naught times the cosine of theta. Right, this is just from projectile motion. We know at the top the Vy is going to 0, and so Vx is constant. That's going to be 35 cosine of 30. And that is whatever it is. And then to find the kinetic energy, I say that's 1/2 of m times v squared. That's going to be 1/2 of the mass, which is 0.2, times 35 cosine 30 squared. And I think that's 92, right? Did I do that right? All right, so 92 joules is the right answer. Very good. C is right. If you did D, that was the next most common answer. If you did D, you just said 1/2 of the mass, which is 0.2, times the speed, which is 35 squared. But you forgot this cosine 30 term, and so that's really important. That's what you get, I think, if you do D. Okay? All right. Make sure you watch the video about conservative and non-conservative forces. You'll see some questions about that either on Friday or definitely on the exam. Okay, let's try this one. This is a conservation of energy problem, a lot like the athlete jumping up with 9 meters per second before. All right, doing really well. Let's wrap it up, about 10 seconds. Stop at 155, 155. These are easier, right, than what we did last chapter? Are these easier? Yeah, you're doing a lot better on them. So here, I have an object that goes up, comes back down again. At the bottom, it only has kinetic energy. At the top, it only has potential energy. And I want to know how high does it go. So I say the kinetic energy initial is equal to the potential energy final. That's 1/2 mv squared is equal to mgh. The ends cancel there and there. And I'm looking for h is 1/2 v squared over g. The answer unanimous is D, 6 or 11.5 meters. Okay. see, I went to the blood van, like where they take your blood, donate blood the other day. You ever go get blood? You should, saves lives. But they told me, they typed your blood. They told me that I had a type A blood. And I knew that couldn't be right. It must have been a typo. All right, good. So we haven't done this, so let me find a problem and we'll work through one. I'm just going to work through this one. It's really similar to what we've done before, but it's just a little bit different. This has to do with elastic potential energy. So you remember I said that there's gravitational potential energy, and then there's also elastic potential energy. That elastic potential energy is equal to 1/2 K times x squared, where K is the spring constant, and that's given up here in the problem. The spring constant is equal to 1,200 newtons per meter, and x is the elongation of the spring. How much do you compress it, or how much do you stretch it out? Now this spring, if you let it oscillate, it will go back and forth, back and forth, back and forth. At what position does it have its maximum speed? At -20, at 0, or +20? Where does it have its maximum speed? Well, what is the speed here when it comes to the very end of this oscillation? It's 0. So at both of these points, v is equal to 0, and v is equal to 0. So at this point, I must have a maximum speed, right? That's where it's going the fastest, when it goes through that equilibrium position. And so I can think about what is the potential or kinetic energy. Here, my kinetic energy is going to equal 0, and my potential energy is going to be at its maximum value. Whereas here, my kinetic energy will be maximum, and my potential energy will equal to 0. And then at the further extreme, 0 kinetic, maximum potential energy. And it's going to oscillate back and forth, changing energy between kinetic and potential energy. I want to know what is the velocity as it passes through the middle at x equals 0. And so I'd say the potential energy from right here will equal to the kinetic energy at right here. So the potential energy is 1/2 of K times x squared equals 1/2 mv squared. Notice the halves cancel, and I'm looking for v. That's going to be kx squared over m, and square root both of it, square root that. So it's going to be the square root of 1,200. 1,200 is this, that's the spring constant, times x, which is 0.2 meters. That's right here. It's in centimeters, so I have to convert it. Divided by the mass, which is 1 kilogram. And that's equal to whatever it is, square root. What is that? I know. Here are lots of buttons. Yeah. Yeah. You think you have it? Huh? Is that what y'all got? 6.9. Cameron? 6.9. Okay, I think that's right. All right. So the answer is 6.9 there. Just like the other problem, like with the athlete that's jumping up and down. But here, instead of dealing with gravitational potential energy, you're dealing with elastic potential energy. All right. There's one other type of problem I want to work through that we haven't done yet that sort of combines some of these ideas. And then really that's the end of this chapter. I would go through and do the, yeah. I don't know. Can y'all tell me the square root of 240? Yeah, that's not 6.9. Yeah. Oh, yeah. It was my mistake, actually, because you have to square this. So it's not the square root of 240. It's the square root of whatever that is. Okay. I'm sorry about that. Thank you for asking. So that would be 6.9. All right. One more type of problem. We'll get out a few minutes early. Let's do this one other type of problem. Let's look down in your exams 3. I think it's like fall 18. Or fall 17. Yeah. Let's do this. This is fall 17 exam 3. When you're looking at these, they're almost always going to be exam 3. Sometimes at the end of exam 2, I got a little bit of work stuff, and so look back at exam 2 as well. But most of them are in exam 3. Here, I have a 10-kilogram kid that comes down a slide. So I have a kid, comes down a slide, says that the slide is 2 meters high, and the kid comes down, and I want to know what is his speed at the bottom. Now, normally the way I'd do this is I would say mgh equals 1/2 mv squared, right? The gravitational potential energy he has at the top is all converted into kinetic energy as he goes to the bottom, and then I can solve that for v. It would be m's cancel, square root of 2gh, which in this case would be the square root of 2 times 10 times 2, the square root of 40, which is, what is that? My square root of 40? 6 point something? 6.3. So that would be 6.3 meters per second. And you see that's an option right here. But this question is asking, what happens if you have a frictional force acting on the slide? Now you can probably tell me what the answer is going to be just right off. What do you think the answer is going to be? It's going to be A, right? Because you know that if you have friction acting on this slide, then the kid will actually slow down as he goes down the slide. Well, let's say that there were a number of answers that were less than 6.3, and we want to figure out what is his actual speed. I know that I have this frictional force acting on that kid for the entire slide. And what do frictional forces do to energy? Do they give or take away energy? They take away energy. So I would rewrite this just a little bit and say mgh, which is the total amount of energy that the kid had at the beginning, and subtract the work that's done by friction, because that's the amount of energy that's been being taken away from that kid. And then that's going to equal to the amount of kinetic energy that he has at the bottom. So let's say mgh minus F times D is equal to 1/2 mv squared. That's going to be 10 times 10 times 2 minus the frictional force, which is 5, times the distance over which it acts. The slide is 4 meters long, so it's going to act over 4 meters, and that's going to equal to 1/2 of 10 times v squared. So it's 200, 180 divided by 5. Square root of that is equal to v. What is that? Oh, it's 6. Never mind. Yeah, of course. 6 meters per second. Okay? This is a problem that has to do with the conservation of energy. That is, the energy here equals the energy here. But then it also applies that idea of the work energy theorem, that if I do work on an object, it changes its energy. And that's what's happening here. That this frictional force is doing work on this kid as he slides down the inclined plane. As you look through exams, let me show you another example. I'm not going to do it, but I want to show you some other examples of that so you can practice. Let's go to the next exam. Like number 5 is a good one to look at. Number 8, number number 5 and number 8. Those are both good ones to look at. You can look back at some of the older exams and you'll see other questions that are similar to that, okay? That's really it for chapter 5. We might have a little bit of time. If you have questions about chapter 5 on Friday, we can have a little bit of time, but I intend to move on to chapter 6. I know that seems fast. That's usually what we do. It's just a short chapter, not much in it. But your next exam will be chapters 5, 6, and then maybe 7. We'll see. Okay? All right. Well, I guess you go up to the financial aid office and tell me you want a refund, because I'm going to let you out in about 5 minutes.